In this video, we are going to talk about DevOps and code management. Let's take a quick look at how things used to be traditionally in software development. In the past, development, release, and support were often handled by separate teams. So you would have one team writing the code, another team responsible for deploying it, and yet another for maintaining it after release. Now, sometimes the original developers might also be the ones who implemented future changes, but not always. In many cases, there was actually a dedicated maintenance team that handled updates, bug fixes, and ongoing support after the initial release. This separation of responsibilities often led to communication gaps and delays, especially when bugs were discovered or new features were needed. It set the stage for more modern approaches like Agile and DevOps that aim to bring these rules closer together. So let's look at this diagram to understand how responsibilities were traditionally divided in software engineering. We typically had three distinct stages: development, release, and support, each handled by different teams. The development team would create and test the software, then hand it off to the release team, which job was to deploy it for real-world use. Once the software was in production, the support team would take over to handle bug reports, user feedback, and any technical issues that came up. These reports have to go back to the development team through support, which adds layers of communication. Now, one of the biggest problems with this traditional model is that it introduces inevitable delays and overhead. Think about it, every issue has to pass through multiple hands. A bug found in production doesn't go directly to the developers. It's first reported to support, then to the development team. So that slows down the response time and often result in miscommunication or even duplicated efforts. This was one of the major motivations for adopting more integrated approaches like Agile or DevOps, where development and operations work more closely together or even as a single team to streamline this feedback loop and reduce delays. All right, so now let's talk about how the industry responded to the delays and communication breakdowns we discussed earlier. One major shift was the rise of DevOps, which is a combination of development and operations. DevOps was designed to speed up both the release process and ongoing support by breaking down the walls between teams. Instead of having separate development and support teams, DevOps encourage the same team to develop, deploy, and maintain their software. That means fewer handoffs, faster fixes, and more accountability. Now, why did DevOps take off so quickly? Part of the reason is the influence of Agile, which had already shortened development cycles. Another reason is what companies like Amazon did. They engineered their systems to be more reliable and scalable, especially as they move to offer cloud-based services. And here is the key. When software is offered as a service on the cloud, it's possible to release updates frequently and seamlessly. DevOps supports this model perfectly by integrating continuous delivery and automated deployment practices. Let's go over three key DevOps principles that guide how teams work effectively. First, everyone is responsible for everything. This means that all team members, not just developers or just operations, share the responsibility for building, delivering, and maintaining the software. So if there is a bug in production, the whole team owns it, not just support or QA. This mindset encourages accountability and collaboration. Second, everything that can be automated should be automated. That includes testing, deployment, integration, and so on. Automation helps reduce human error, saves time, and ensures consistency across environments. And third, measure first, change later. This is crucial. Before tweaking tools or workflows, you need data. DevOps is very metric driven. We collect information about system performance, deployment frequency, failure rates, and more. These three principles are at the heart of why DevOps work in fast-paced, high-demand environment. Let's wrap this up by highlighting some of the main benefits of DevOps approach. First, we get faster deployment since DevOps break down the communication barriers between development, release, and support. The time it takes to push code into production is dramatically reduced. Second, there is reduced risk. DevOps encourages small, frequent releases rather than big, risky ones. So each new update is a minor change, which makes it easier to spot problem and prevents one bad feature from crashing the entire system. Next, we have faster repair because DevOps team are cross-functional and collaborative. There is no need to figure out which team is responsible when something goes wrong. The team as a whole takes ownership, which means issues get fixed faster and with less finger pointing. And finally, teams are more productive and happier. Why? Because they work more collaboratively, see the direct impact of their work, and avoid the stress of siloed responsibilities and unclear expectations. As software development progresses, teams get complex quickly. Teams write thousands of lines of code, build automated tests, and work with hundreds of files, libraries, and tools. So how do we keep it all organized and under control? That's where code management comes in. Code management refers to the practices and tools used to handle a growing, constantly evolving code base. It's not just about storing files. It's about making sure that changes from different developers don't conflict, that you can roll back if something breaks, and that you can build different versions of the product easily. Modern code management tools like Git and platforms like GitHub or GitLab helps us to all of that. They let us compile code into executable files from various source files and run automated tests to verify the software still works after changes. Without proper code management, collaboration breaks down and releases become chaotic. Let's walk through a realistic and unfortunate scenario that shows what can go wrong when proper code management and collaboration practices are not followed. Alice and Bob both were developers at a company called FinanceMadeSimple. Alice was working on fixing a bug in a module called tax return preparation. What was the issue? So the software was saying a tax return had been filed, but in some cases it actually hadn't been sent to the tax office. Serious problem, right? So she fixed it. Meanwhile, Bob was also working on the same module, but on the user interface side. Here is where things went wrong. Bob made a copy of the code before Alice made her fix. He did his UI changes and saved the file, which unknowingly overwrite Alice's fix. Neither of them realized this had happened, and because the bug was intermittent, the automated test didn't catch it. So the product shipped with the bug still in it. Now what happened next in a chain reaction? For most users, the system worked fine, but for a small percentage, their tax return weren't filed, and they got fined by the government. When this hit the news, it was discovered that the company had been negligent, leading to fines, a loss of user trust, and eventually the failure of the company itself. Alice and Bob both lose their jobs. So, what's the takeaway? This story illustrates exactly why we need version control communication and automated checks in place, especially when multiple developers are working on the same code base. So now that we have seen what can go wrong without proper coordination, let's talk about how DevOps addresses that risk, starting with code management. In DevOps, having a code management system like Git is absolutely essential. Why? Because it's the backbone that supports the automate everything principle. We can't automate testing, deployment, or monitoring if your code and its history aren't being tracked in a centralized, reliable way. But code management doesn't just store source code, it also stores important configuration files, build scripts, and even documentation. It becomes the single source of truth that all other DevOps tools rely on. Automation tools like GitHub Actions and monitoring tools, they all need to interact with the code management system. They pull code from it, run tests based on it, deploy based on it. Without it, the entire DevOps pipeline falls apart. So in short, code management isn't just about tracking changes, it's what makes DevOps work smoothly, efficiently, and safely. This diagram gives us a big picture view of how everything connects in a DevOps workflow, with the code management system right at the center. Let's start with the core. The code repository, this is where your code lives. It supports branching and merging, which means developers can work on different features or fixes without stepping on each other's toes, and later combine everything safely. It also handles versioning, so you can track changes, roll back, or recover earlier versions of the code if needed. Now everything flows through this system. On top, we have DevOps automation, things like continuous integration or CI, automatically building and testing code every time someone makes a change, and continuous deployment or CD, which is automatically pushing those changes to production. Continuous delivery, which the ability to release updates at any time reliably. And infrastructure as code, managing servers and environments using code stored in this repository. These automation tools constantly pull from or push to the code base to do their jobs. Below, we have DevOps measurement. This is where we collect data on how the system is performing, run analysis, and generate reports. These tools also rely on the code repository to track performance over time and associate results with specific code changes. So you can see the code management system is the glue that connects everything. It's not just for organizing code, it enables automation, collaboration, and data-driven decision making across the DevOps pipeline. This slide highlights some of the key benefits and capabilities of a modern code management system, especially in the context of DevOps and collaborative software development. First, we have version and release identification. Every time you submit code to the system, it assigns a unique identifier to that version. That means at any time you can go break and retrieve a specific version based on its ID or its attributes, like who submitted it or when. This is essential for traceability and debugging. Next is change history recording. It's not just about tracking what changed, but also why. Most systems require you to write a commit message explaining the reason for the change. Over time, this builds a historical record of the evolution of your software, great for accountability, team learning, and audits. Then there is independent development. Multiple developers can work on the same file without stepping on each other's toes. The system doesn't overwrite anyone's work. Instead, it creates new versions of each submission. When conflicts arise, the developers can merge changes together truthfully rather than losing work. And finally, these systems are storage efficient. Instead of saving full copies of each version, they use delta storage, which means they only store the differences between versions. This keeps your repositories lightweight even as your project grows. All of these features work together to make development collaborative, safe, and scalable. This is fun and important bit of history in the world of software development. Back in 2005, Linus Torvalds, the creator of the Linux kernel, developed a tool that would completely change how we manage source code. That tool was Git. And believe it or not, he created the first working version over a single weekend. That motivation was to support the Linux open source community, which involves many developers from all over the world. Linux needed something fast, reliable, and distributed, and most importantly, something that didn't rely on a central server. So Git was born as a distributed version control system. Unlike earlier tools that used a central repository, Git gives every user a full clone of entire repository, every version, every file, every branch on their own machine. This was made possible because by 2005, storage was getting cheap. So it was no longer a big deal to keep full local copies of code bases. That design made Git incredibly resilient, fast, and perfect for collaborative open source work. And just as a cool fact, Git actually started by hosting its own code base as its first repository. So Git was managing Git from the beginning. This diagram helps us understand one of the most powerful features of Git, distributed repositories. At the top, we see the shared Git repository. This is often when we host on platforms like GitHub. Inside the shared repo, we have a master branch. This is the main line of development, and we also see a couple of featured branches. Branch 1, branch 2. These branches contain specific sets of files that were changed independently. For example, branch 1 contains files F7, F9, and F21, while branch 2 contains F2 and F3. Now let's look at the bottom of the diagram. Alice's repository. When Alice clones the repository, Git doesn't just give her the current version of the files. It gives her everything, the full commit history, the branches, and all files from master branch. That's why Git is called a distributed version control system. Every developer has a complete local copy of the entire code base and its history. That means Alice can do everything locally, create new branches, explore the commit history, and test changes without needing to be online or connected to the central repo. Once she's ready, she can push her updates back to the shared repository for others to review or merge. So this model not only supports powerful collaboration, but it also enables resilience and independence in each developer's workflow. All right, this slide walks us through the basic Git workflow, and it's a great reference for beginners learning how to manage code with Git and GitHub. We are starting on the left with your repository folder. This is just your local project directly with all your code files. When you make changes here, Git doesn't automatically track them. You first have to stage the files. To stage changes, we use git add dash dash all. So this tells Git, hey, I want you to watch these changes. The files move into the staging area where they are marked as ready to be saved. Next comes the commit step. This is like taking a snapshot of your project. You are saving a point in time version of the staged file into your local Git repository, your personal version history. We do that using git commit-m, and inside quotation you write your message. The -m flag lets you write a message describing what you changed. This is important for understanding your commit history later. Then, when you are happy with your changes and want to share them with others, you push them to the central repository like GitHub. Git push origin master. This sends your local commits to the remote repository, what GitHub calls the origin. Other team members can then pull your changes into their own local repository. And finally, if you're ever unsure of what state your repo is in, what's being changed, staged, or committed, you can run git status. This command will tell you exactly where you are in the workflow and what Git is expecting next. So remember this cycle: add, commit, push, and check your status often. All right, this diagram does a fantastic job of showing us what's really happening behind the scenes in Git, especially how files and code changes move through different areas of the system. Let's break it down step by step. On the left, we start with the working tree. This is your actual project folder with the files you are editing. When you have made changes and you're ready to track them in Git, you use git add. That moves the changes into the index or staging area, which is like saying I'm planning to include this in my next commit. Then to finalize those stage changes, you run git commit. This takes everything in the staging area and saves it into your local Git branch. So far, all of this is still on your computer only. Now, if you want to share your changes with others on a platform like GitHub, you use git push. This pushes your commits from your local branch to the remote repository, which lives on GitHub, GitLab, or Bitbucket. It also updates the remote tracking ref. This is Git's way of keeping track of what the remote branch looked like the last time you synced. If someone else has pushed changes to the remote and you want to bring those updates into your local repo, you can use git fetch. This grabs the changes but doesn't apply them yet. To actually apply those updates to your working files, you would then use git merge or git rebase. Alternatively, you can do both in one step by running git pull. This fetches and then merges changes from the remote into your local branch. And let's not forget git checkout. This command lets you switch between branches or go back to a previous version. So this diagram helps you visualize the flow of data between your files, Git internal structures, and the cloud hosted repo. And once you understand this, Git starts to feel a lot more predictable and manageable. Okay, now let's time to talk about GitHub and its actions. So in this slide, will give us a snapshot of what makes GitHub such a central hub for modern software development, especially in open source communities. At its core, GitHub is an open source code repository hosting platform built in Git. But it does much more than just store code. Let's go over some of the key features. Code browsing, which you can easily navigate through files and directories online, view commit history, and even compare branches visually. Issue tracking, that every project can have a list of open issues, bugs, feature requests, questions that helps organize collaborative work. Wiki pages, these provide an area of documentation, setup instructions, FAQs, and anything else that team wants to document. Ignoring files, you can use .git ignore files to exclude temporary or sensitive files like compiled binaries or credentials from version control. Beyond these tools, GitHub also serves as a social network for developers. You can follow users, start repositories, fork projects, and build a visible portfolio of your contributions. This visibility is a big part of how developers collaborate, learn from each other, and even get hired. And while GitHub is the most well-known platform, there are other storing alternatives like GitLab, which is a very popular for its built-in CI/CD tools. Bitbucket, which integrates closely with Jira and other Atlassian tools. We have also, for example, Git, a lightweight self-hosted Git service, AWS Code Commit, which is great for teams already inside the AWS ecosystem. So whether you're working solo with a small team or contributing to open source platforms like GitHub makes collaboration and visibility much easier. Let's wrap up by looking at some of the key advantages of using a distributed version control system like Git. This really helps explain why Git has become the standard tool for modern software teams. Resilience. So first, Git provides resilience. Everyone who works on a project has a full copy of the repository, including the entire history. So even if the central shared repository is lost, saying in a cyber track or system crash, the project isn't gone. Any clone from a developer's machine can be used to rebuild it. Also, since your full repo is local, you can keep working offline, on a plane, in a remote area, or even during a Wi-Fi outage. And about the speed, most Git operations like Git add, Git commit, and Git log are local. That means they are almost instantaneous because there is no network delay involved. You are not waiting on a server somewhere to save your changes. And finally, we have flexibility. Developers can freely experiment locally, create branches, test new ideas, or try refactors without affecting anyone else's work. Only when you're happy with your changes, push them to the shared repository, making it visible to others. That balance of private work and global collaboration is hard to achieve in centralized systems. So overall, Git gives us reliability, performance, and creative freedom, and that's why it's the go-to system for teams of all sizes, from hobby projects to major tech companies. This diagram illustrates how GitHub repositories can be organized across multiple collaborative projects. At the center, we have GitHub, which acts as a hosting platform for version control repositories, here labeled RP1 through RP4. Each of these repositories belongs to a different project. Now let's look at how the projects connect. Project 1 is associated with repository RP1, and within that project, you can see see multiple contributors or components RP1A, RP1B, RP1C, and D. These could represent team members or modules within that repo. Project 2 is connected to repository RP2 with contributors or subunits labeled RP2P, A, and R. Similarly, project 3 is linked to RP3 and project 4 to RP4, and each with its own set of internal contributions. This structure reflects the real-world workflow where different teams or project groups work on separate GitHub repositories. But those repositories are hosted on the same platform and can be managed collectively. For example, by an instructor in a course or by a company managing multiple software products. The double arrows shows that there is two-way collaboration between GitHub and each project. Projects push code to GitHub and pull updates from it. This is how GitHub supports version control, collaborative coding, and remote team integration all at once. So in short, GitHub acts as a centralized space where many projects can live, each with multiple contributors, and everything stays versioned, organized, and accessible. Let's close with one of the most essential features of version control, branching and merging. In any modern code management system like Git, branching lets you create a separate line of development. So if Alice or Bob want to try a new feature or fix a bug, they can create a branch and work independently from the main project. Think of a branch as a sandbox, a safe place to experiment. You can make changes, test things, even make mistakes, and none of it affects the rest of the team's work. Now, what happens when Alice or Bob finish their work? They don't just copy and paste it into the master. Instead, they use a process called merging. This carefully integrates changes from their branch into the master without overwriting other works. Git makes sure that if two people change the same file, you must resolve any conflicts before the merge is complete. And one of the best things about working in a branch is reversibility. If something goes wrong, Alice can easily roll back to the master's branch. Or if she's made several commits and needs to undo just the last few, Git lets her to do that too. So in summary, branching gives freedom. Merging brings collaboration. Git ensures safety. And that's why branching and merging are fundamental practices in every successful software project today. Let's clarify an important distinction in GitHub-based collaboration, the difference between the fork and a branch. So when you're working as a part of a team on a shared project like Alice and Bob, you usually create a branch. A branch is just a lightweight, independent line of development within the same repository. It lets you work on new feature or bug fixes in isolation, safely experiment without impacting the main or master branch, easily merge your work back into the main code base. It is great for internal collaboration where all developers have permission to push and pull from the same repository. A fork, on the other hand, is used when you're contributing to a project that you don't own. For example, an open source project on GitHub. When you fork a repo, you create an entire copy of it under your own GitHub account. From there, you can make changes independently, create branches and commits in your own copy, eventually submit a pull request to propose your changes back to the original repository. Forking supports external collaboration where you don't need direct access to the main project. So at the final talk, use a branch when you're part of the core team and have direct access to the repository, and use a fork when you are an outsider contributing to someone else's project. Okay, so thank you very much for watching this video, and we'll continue in the next video. Thank you and bye.